Quantum computing is always presented as a magical warp drive for processing power. We hear that because qubits can exist in a superposition of 1 and 0, they can compute every possible answer simultaneously. But behind the headline-grabbing algorithms lies a massive engineering moat. The reality is that today's quantum computers are fragile, noisy, and incredibly hard to program. In classical computers, a bit is a binary switch, 0 or 1. A qubit is a mathematical vector, represented on a sphere. By using superposition, n qubits can represent 2 to the n states simultaneously. If you have 300 perfect qubits, you can represent more states than there are atoms in the observable universe. But a qubit is also extremely sensitive to heat and electromagnetic interference. When thermal noise hits a qubit, its quantum state collapses, a process called decoherence. To run a useful algorithm, we need logical qubits, error-corrected virtual qubits made of thousands of noisy physical qubits. This physical-to-logical ratio is the single biggest bottleneck in quantum hardware scaling today. Building a quantum computer requires a massive system stack. At the bottom are the physical qubits, cooled in dilution refrigerators to a fraction of a degree above absolute zero. Above them lies the microwave control hardware, then the error correction runtime. Finally, compilers translate quantum algorithms into instruction sets. To make progress, we must design across the entire stack. Look at how we actually program these machines. This is OpenQASM, the assembly language of quantum circuits. We don't write loops or conditionals. We manipulate individual qubits with electromagnetic pulses representing quantum gates. Here, a Hadamard gate puts a qubit into superposition, and a controlled knot entangles it with another. It's a completely different programming model. This brings us to the mindset gap. Classical programmers think in terms of step-by-step logic, loops, and state changes. Quantum programming is about manipulating probability amplitudes so that incorrect answers destructively interfere and cancel out, while the correct answer constructively interferes, raising its probability of being measured. It is applied linear algebra. Even if you write a perfect quantum algorithm, compiling it is a nightmare. Qubits on a chip are physically arranged in a fixed grid. If your algorithm requires entangling two distant qubits, the compiler must insert a series of swap gates to move the states next to each other. Every gate adds noise, meaning the compiler must continuously optimize gate counts to prevent decoherence. This is where artificial intelligence enters the equation. Machine learning is actively accelerating both quantum hardware design and compilation. In hardware, AI models predict stable topological materials and calibrate control pulses. In software, reinforcement learning optimizes the nitrogen monophosphide hard routing of qubits, finding the most efficient path before decoherence collapses the system. Despite these challenges, hardware milestones are accelerating. In late 2024, Google introduced its Willow processor, demonstrating a massive step forward in quantum error correction. By expanding to neutral atom hardware alongside superconducting qubits in early 2026, Google is diversifying its physical platform to scale toward fault tolerance. IBM has taken a different approach, quantum-centric supercomputing. Their 2026 roadmap centers on integrating their Nighthawk processors with classical, high-performance compute clusters. With a major $10 billion investment and the construction of their Anderon wafer foundry, IBM is targeting a fault-tolerant system named Starling by 2029. Microsoft is pursuing topological qubits, which are theoretically immune to certain types of environmental noise. In June 2026, Microsoft announced its Majorana 2 chip, claiming a 1,000-fold stability improvement over Majorana 1. By leveraging topological protection, Microsoft aims to deliver a scalable quantum system by 2029. However, Microsoft's claims have sparked intense scientific debate. In late June 2026, a critique published in the journal Nature by Dr. Henry Legg identified software bugs and data ordering errors in Microsoft's topological gap protocol. While Microsoft dismissed these as minor, it highlights the extreme difficulty of verifying quantum states. Where will these systems actually be useful? The killer app is molecular simulation. Simulating the exact quantum behavior of a molecule with more than 50 electrons is impossible for classical supercomputers. Quantum computers can simulate this naturally, transforming drug discovery and material science. Trapped ion systems, like those from Quantinuum, are showing the highest gate fidelities. Reaching 99.9993% fidelity is critical because it reduces the physical to logical qubit ratio, making error correction practical. Quantinuum is aiming for its fault-tolerant Apollo architecture by 2030. The verdict is clear. Quantum computing is not a drop-in replacement for classical CPUs. It is a coprocessor for highly specific physical simulations. The timeline to commercial utility is a marathon through materials, science, control electronics, and developer mindsets. Keep your eye on the stack, not the hype.